thank you for being here with me. It's my first time speaking here at NewCrafts, and I'm super excited, but I'm also super scared. But it's going to be okay. I already feel better now that you know that I'm super scared. So yes, today we'll be talking about cybersecurity, but in a perspective that we don't usually see as software developers and people working in software in general. We tend to see cybersecurity through the lens of software vulnerabilities. And it's a very narrow scope, but it is our scope because software vulnerabilities are the things that we fix and sometimes also the things that we introduce, but that's another topic. But there's so much more to the field and to cyber attacks, and this is what we're going to see together today. So my name is Sonia. I recently joined Arola as a consultant. So very briefly, so Arola, for those who don't know, is a consulting firm, and we provide expertise in different formats, being like consulting, coaching, training, and project delivery. All of that with a craft DNA in everything that we do. We have a booth upstairs. If you want to know more, feel free to come by in between sessions and say hi. So this is my day job, and this is my weekend job. Well, it's not really a job, but it's a big part of my life, and it's Capture the Flag, or CTFs. CTFs are cybersecurity competitions where you have to solve challenges in different categories, but the goal is always the same. You have to retrieve a file or a message, something that you're not supposed to have access to. That's what we call the flag. And I've been doing this for 6-7 years now. And most of the time, to do so, you have to exploit software vulnerabilities, but not always. And realizing that has been the main motivation for this talk. But before we dive into the technical details of all of this, I have a little bit of story time for you. So a few years ago, when I first moved into my first apartment, I went to look for furniture. And most specifically, I needed something for my television. So like many people in Paris, I went to IKEA and I stumbled upon this. It's a cool TV storage unit because it has two features. The first one is that it can accommodate a large TV. And the second one is that it has a reinforced back panel made to hold a flat screen TV. And when I was doing my research on the internet, I saw that usually the people who would have small TVs would mount them onto the back panel, and the people with larger TVs would just place them on the shelf. But one question remained: can we do both? Because nothing in the spec of this piece of furniture says that I can't do that. So can I actually mount a super large TV on this reinforced yet super thin back panel? When I'm asking that question, what I'm doing is questioning the design of it, of this piece of furniture, or the spec, questioning whether we should know explicitly or instead of like relying on common sense. And surprisingly, I didn't find the answer to that question online. I didn't have a definitive answer, like a yes or no, not even a maybe. Usually the answers I would get would be like, I don't know, because I don't use it as a TV storage unit anyway. And that would be the answer of a community called IKEA Hackers. So it's a bunch of people that will assemble, disassemble, remix, and customize IKEA furniture to suit their specific needs. And so, for instance, they will take that piece of furniture and turn it into individual lockers and storage space for their family of 4 kids. Or maybe they will take this piece of furniture and they will rotate it 90 degrees to the right and put a bed inside it and benefit from the extra storage space around it. So nothing to do with my TV. They don't really care about that. And this behavior has a name. In ergonomics, we call this catachresis. It's the fact of using a tool in a way that significantly departs from its conventional or traditional usage. And you don't have to be an IKEA hacker to do that. You've probably done this before if you've used, for instance, a lighter, to open bottles, or if you've used the pointy end of a knife in lieu of a screwdriver. And the cool thing is that catachresis is not always a consequence of design flaws. Like, these people didn't turn this piece of furniture into lockers because it was bad at being a TV storage unit. It does a great job. I'm very happy with it. It's just two things that can coexist together. It's two separate statements. And where am I going with this? Well, in the same way, attack vectors are not always a consequence of vulnerabilities. Sometimes we will rely on very legitimate tools, objects, protocols, just in a way that significantly departs from their conventional usage. And today, I want to show you 3 techniques that we can use, and 3 tools that we can use in unintended ways in the context of complex cyber attacks. And we will start off very strong with something very famous called domain name system, or DNS. So very briefly, DNS, I'm sure most of you know how it works, but let's summarize this very quickly. So DNS has been here to, at the beginning, to map domain names to IP addresses, because IP addresses are hard to remember, names are easier to remember, so we have this kind of huge phone book for the internet. And so the way it works is, let's say that, for instance, I want to know where the domain fr.wikipedia.org maps to. I need to ask my question to someone, and that someone will be what we call a DNS resolver. It's a very specific type of DNS server, and it knows nothing about anything, but it knows how to ask questions. So I ask my question to it, where can I find this? And the first type of server it would ask that question is the root servers. There are very small numbers of root servers in the world, and they don't know the answer to that question. But what they know is that the name servers in charge of the .org domain might know more about it. So the search continues. They just gave me the address of another server I can ask my same question. So I ask it again. And the .org name server will tell me, I don't know, but the servers in charge of wikimedia.org, they might know about it. And so we keep on going until we finally get the answer. And so this is our answer of where we can find fr.wikipedia.org. It actually maps to another domain name, and then which maps to this IP address. And what we could have done also is, if we here already knew who to ask, we could have asked them directly and completely just bypass the front desk in a way, and just ask a question directly, and we would get the same result. It's also an appropriate behavior when it comes to DNS. And so what we see here, the answer to our question is what we call DNS records. There are many different kinds of them, but some of the most common are the A record that gives you the IPv4 address of a server, the 4A record, same thing for IPv6, C names, we've seen it before for the redirecting to a different domain, and TXT that could be anything as long as it's text. So now that we know the basics of how all of this works, then we can start working on something called DNS tunneling. So let's imagine we have this computer, and it sits inside this beautiful square that is, rectangle, that is an enterprise network. So it's completely sealed off. That computer is not accessible from the outside. We cannot reach it from the outside. And imagine that this computer actually got infected somehow by some malware, but the process of how it got infected doesn't really matter here. The thing that matters is that in order to keep on working, this malware needs to communicate information to a command and control server that belongs to the attacker, and it's reachable at attacker.com, for instance. So command and control, that we call also C2 server, cannot call the computer directly. So we have to find a way to reach the C2 server from the inside of the network. One of the reasons we might want to do that is to signify to that server that we are ready for what's next. Like, we are inside the machine, what do we do now? And so how do we do that? Well, maybe we can craft some sort of message to say, hey, I'm ready. Well, it has spaces and everything, so we just convert all of this to hexadecimal to make sure that it's easier to send. And then maybe we put that inside of a ping, and we try to ping attacker.com. And we try, but nothing comes back. It didn't go through. And the problem is that between us and the C2 server sits the company's firewall. And the firewall dictates what goes in and what goes out of the network. And well, we might think that as a computer inside here, you have no business pinging stranger out there. So we should just block that. But what we realize is that when trying to ping attacker.com, we managed to resolve the domain name into the corresponding IP address. So that means that most probably the DNS traffic can go through. And so what we could do instead is just try to make an innocuous request to ready.attacker.com. And this way we can, this is our cue to the C2 server to say, okay, I'm ready for what's next. So now that we've managed to establish communication between the two computers, what can we do with that? Well, as we said before, we can receive instructions. Because what to do next? Well, it depends. I mean, you created this piece of malware and then you just yeeted it into the wild and hoping it would land somewhere. And it did, but the where makes all the difference. Like, if I ended up on some sort of company's critical infrastructure, then good, I might want to stay here and explore a little bit more. But maybe I landed on a super heavily monitored machine that belongs to a cybersecurity researcher, and I don't want to be examined by that, so I would not want to stay here. But my C2 server doesn't know where I landed, so I have to communicate that to him. And so what I would do is, as a piece of malware, is gather some information about the computer I'm in, about the domain, some other unique identifiers, what kind of processes are running on that machine, put that into a big string, and query a domain name that will look like that. So I do this request to attacker.com. Now our C2 server kind of behaves like a DNS server, and it replies with an IP address. And that looks like basic DNS, right? We said we ask for an A record, we get an IPv4 address back. This is very legitimate stuff, except this is not a real IP address in the sense that this is not the IP address of a server I should contact next. This IP address was meant to fall through a bunch of its if statements inside the malware's code to say that if this IP falls into this IP range, then it means that I can proceed with the next instructions. If it falls into this other IP range, then maybe it's too dangerous and just erase everything from this computer, like erase your presence from this computer. Or finally, otherwise, well, just stand by and ask again tomorrow. Another thing you can do is deliver malicious code. Like, if we wait and ask for the next day, like sometimes in those super complex cyber attacks, the malware is going to stay for weeks on the machine before actually being activated. So it runs the risk of being detected. And if we get caught, we don't want to be caught with our best secrets. Like maybe we have this super secret zero-day exploit that no one has ever seen before, and I don't want to leave that on the machine and disclose it to everyone. So I really want to retrieve this at the last minute. So that's why we have this code that we call a stager. It's a piece of code that lands on the malware and acts like a scout. So it scouts the terrain, and then it sets the stage for the payload, which is the dangerous part of the malicious code. And then it downloads it. But we're not going to download that over HTTP because that's a huge red flag. Like the firewall is going to say, "What the hell is this address? I don't want to deal with that." Maybe they even block it. So what we do, let's say a very simple example of a stager could be a very simple script. It's one line of bash, and what it does is it performs an NS lookup, a DNS request, and it asks for a TXT record for this domain. And whatever comes out as a response, it executes it straight away. So we perform our request, and whatever we get as a response, we run it. So in reality, it's a little bit more complex than that. You need more complex scripts, and the TXT records are very limited in size. And if they're too big, like they can be quite big, but then it becomes suspicious because that's not how we usually use them. So what happens is that the script that we download is actually split into multiple records, and the stager will download them one at a time and then regroup everything together. Oops. And the last thing you can do is, once you've done everything you wanted, maybe you found some credentials, some interesting secrets that you want to exfiltrate to the C2 server. And, well, same as before, same as step 1. We convert this into some sort of hexadecimal string, and then we query this completely random domain. It's not really random, like it's literally the string that we have here, and we send this request to the C2 server. And we don't really care about the response. What we care about is that this request is logged somewhere. As long as it logs somewhere here, it means that we can parse it and retrieve the secret afterwards. And most of the time, you don't send it just like that. You will encrypt it because modern firewalls will try to parse every string that looks like hexadecimal base 64 to try and see what's inside and if it looks suspicious. So if you encrypt it, you might evade this kind of controls. So these are some of the things that you can do with DNS. You can do many other things, but I don't have time in this presentation. I could actually do a talk on each and every one of them, but choices had to be made. The second tool that we can use is something that text and image. It's really at the core of everything that we use in our modern web. We have text and images everywhere. If we consider from a digital standpoint, and this is very basic stuff, like I'm not teaching you anything, but an image is just a bunch of pixels, and every pixel has a color, and this color is represented in some sort of way, maybe RGB, so a certain amount of red, green, and blue, and this amount is encoded on 1 byte for each one. And once I have all this pixel information, all this color information, I compress it in any way I want. It can be lossy compression, lossless compression. I add metadata around it, and voila, I have my image file. So this is described with image file formats and specifications, super long RFCs about it. But that's how it works. And for the text, well, it's pretty much the same. We have many ways of representing this capital A depending on how we encode it. So we can use UTF-8, and then it takes up a byte. UTF-16 would take 2 bytes. Base 64 would be something in between. But all of these are representation of the same character. So we have many things we can choose from. And how are we gonna use that? Well, we're gonna use a technique called steganography. So steganography, I really love that. It's the art of concealment, not to be confused with stenography, which is the super fast note-taking technique. And steganography is all about hiding in plain sight. And it doesn't have to be computer related. Like if you take this drawing, you can see that there are a bunch of weeds near the river. Some tall ones, some shorter ones, and well, this is actually Morse code that has been hidden inside the image, with the taller weeds being the dashes and the shorter ones being the dots. With text and images, we can do a lot of things. Like this is actually, it has its very own CTF category where you can hide. Challenges would include hiding text inside audio, hiding text inside text, hiding text inside images. So how do we do? How can I hide secrets in images, for instance? One of the techniques is hiding it inside pixels. So this is the representation of our capital A, binary representation, UTF-8. If I want to turn this into decimal representation, then I get 65. But if I were to change this bit from 1 to 0, then I would get 64. This is the least significant bit. It's the one that brings the least impact on the byte value when it changes. And we can use that, apply that technique in our pixels. So let's take this pixel that has some values of RGB. Let's take 3 of them. Here's the binary equivalent, and here is our capital A. So all we have to do is replace the least significant bit of each RGB of each pixel with the bits of our capital A. And so the consequence of this is that it slightly changes the value of pixels, but our eyes cannot make the difference between a 255 red and a 254. So we can't really see it with just a naked eye. And this is a technique to hide, like for instance, like before, entire archives inside of images. And you can't do that with every file formats. You can do that with PNG because it has, for instance, lossless compression. So you will get your pixels back when you decompress. But with JPEG, those kind of little nuances would be completely overwritten by compression. You have to use different techniques if you want to hide secrets inside JPEG images. You can also hide secrets in text. Like these looks like 2 copies of the same sentence, but one of them is significantly larger than the other one. And that's because it contains my secret message. So if I open this text inside a code editor, for instance, what I'm going to see is that there are many things going on between my words. And if I open this into a hex editor, well, that's the beginning of it. And what I see here is some uncorrelated bytes, and then 2 patterns that seem to repeat on and on. Those two patterns are actually Unicode characters that represents invisible spaces. They are useful, but they're invisible. They don't take any space. And so those 2 characters actually act as our 0s and 1s. So if I replace them with 0s and 1s and concatenate all of this together, well, I get a null byte, but I also get the UTF-8 representation of my capital H, which is the beginning of my secret message. And you can make this a little bit more discrete by using more of these weird invisible characters. And maybe you could use 4 of them and encode pairs of bits instead of single bits, so that it would take less space, because with one character you would encode like 0, 1 instead of having 2 characters, 1 for 0, 1 for 1. Also, you don't have to be super fancy about your steganography techniques. Like this is an example of malware. If you, like, suppose that you have some malware that communicates with a C2 server via HTTP after some point. And maybe sometimes the server responds with this kind of XML body that might look like something legitimate inside of the context where it's used. And you see things like keys, public key token, hashes, and this really looks like a hash. But the thing is, it's not really one. These are 3 parts of an instruction. So like when you put all those hexadecimal values together, it turns into an instruction that can be interpreted by the malware's code into what it should do next, what its next execution. So this is also another form of another way of hiding secrets in text, but really hiding it in plain sight for this time. Well, and these are only just a couple techniques. You can also hide secrets inside base 64 strings. You can recently I've seen secrets hidden in inside assembly instructions. So it's the only limit is your creativity. You can come up with pretty much anything. And so the last tool I want to show you is it's not really a tool per se. It's so something I call feedback, for lack of a better word. If you have one, then feel free to let me know. So what do we mean by feedback? So first, there is what I call the controlled feedback, and it's all the intentional feedback that we put inside our system. Like we put it with purpose. When you take the example of user experience and user reassurance, let's say you have your web app and it's working hard on something. So you put this spinner on the screen to signify to your user that, don't worry, we are working hard on your stuff. You can also have this kind of visual feedback that tells you that, hey, the payment was successful, was declined. And if you want to go to the hardware side of things, then maybe you have this this power button on your computer, like this LED that is on to signify you that the computer is on. So this is feedback mechanisms that we implement on purpose. But there is also what I call uncontrolled feedback, and it's when your system speaks on its own. Like if I take my power button, so it has an LED, and this LED is drawing power from the power supply of your computer, just like the CPU, just like the GPU. And sometimes the rest of your computer will need a little bit more power because it's working harder, and maybe you won't have enough power that reaches the LED, and so it will start flickering, for instance. Or if you take hard disk drives, they will make some noise when reading or writing, and that's not on purpose. I mean, it's a mechanical consequence of how these things are built. Another interesting example is the response time of a server. Sometimes it would respond faster, and sometimes it would respond slower. And it seems like nothing. We can say sometimes because the server is busy doing so many things, responding to so many requests, and that's why. But sometimes it's a little bit more than that. Let's take, for example, an authentication service where you have you enter the username, the password, and then you submit everything. And the code is, and so username and password are checked in the backend. Let's say you have your system that checks the username first, but checking the password is a little bit more complex. You have to hash it and then compare and everything. Maybe we don't want to bother doing that if the username is already wrong. So, or if it doesn't exist, for instance. If you're an attacker, you can actually listen to this kind of feedback and like try different usernames because you don't know, you're not supposed to be on that platform. So you try different usernames, and if you see that one of them makes the server slower to respond, but consistently over time, like every time for this username, it takes longer for the server to respond, then we might infer that we passed the username check and that it takes longer because it's actually working on the password check. And so without even referring to any kind of SQL injection, we managed to guess a list of valid usernames or valid users of a platform. So if those usernames are email addresses, maybe we have potential clients that then we can target with a very specific phishing campaign coming from this type of software they use, and so on. This is called a timing attack, and it's the one example of a broader family of attacks called side channel attacks. So side channel attacks are about leveraging this uncontrolled feedback from your system. Most of the time it's hardware feedback. So your algorithm might be super secure, super robust, it's tested, it works, but the hardware is the one betraying you in this case. One of the good use cases of those attacks is modern cryptography, because we try to make those algorithms secure, and in cryptography, we want to follow this principle of having the secrecy of your message relying only on the secrecy of the key. So the algorithm is public and it's robust, and when it's well implemented, you can't brute force your way out of it. If you receive an encrypted message, you need the key to decrypt it. You can't just guess it. So one of your goals will be to retrieve the key, no matter how. And to illustrate that, we'll take the example of the RSA encryption system. So RSA is a symmetric cryptography, so it relies on a key pair, a public key, and a private key. So public key is public, it's shared with everyone, and it's used to encrypt the message. Private key is private, it never leaves the server. And it's here to decrypt the message that we receive. And to do so, it performs some mathematical operations. So if you want to encrypt a message, you take your message and you raise it to the power of E. And if you want to decrypt a message, well, you take your ciphertext C and you raise it to the power of D. So what does it mean, raising a message to a power of a key? Well, all of this is just a bunch of zeros and ones. It's binary. It's base 2. If you want to see it differently, you can convert it to base 10, and it becomes a huge number, both for the message and for the keys. So what I'm interested in is not this modulus part. We won't talk about that, but we will talk about performing C to the power of D to decrypt our message. And for that, let's take the example of 3 to the power of 5. The naive way of doing this would be 3 times 3 times 3 times 3 times 3. And this is 4 operations. But unfortunately, this is my exponent, and I don't want to be doing 3 times 3 times 3 this amount of time, because I want to be able to decrypt my message before I die. So I need to find a better way. One way of doing it is seeing this computation a little bit differently, and saying that first we will compute 3 times 3, which is 9, and then we do 9 times 9, which is 81, and finally 81 by 3. So we went from 4 operations down to 3, which looks like nothing, but for our previous big number, we went from this big number to like a couple thousands of operations, which is way more manageable. So let's do that again, but we will look at the binary version of a binary representation of the exponent at the same time. So we said we'd do 3 times 3 first, and then we'd do 9 by 9, and then we do 81 times 3. So this is our final exponent. And what we realize is that to go from 1 to 1, 0, we squared, and to go from 1, 0 to 1, 0, 1, we squared and then multiplied. This is why we call this algorithm square and multiply. And so the way it works is you take your big private key, you convert it to binary, and then you pass it bit by bit. And when you land on a 0, you square. When you land on a 1, you square and multiply. So one of the most common side channel attacks is a power analysis attack, because performing all those cryptographic operations actually has an impact on the CPU power consumption. And if you record this and analyze it, then maybe you'll notice that sometimes it takes a little more power, and sometimes it takes a little more power, but for something that looks twice longer than before. And what we realize is that this is when you square, and this is when you square and multiply. So if you pass the power consumption of the CPU, then you can see that, okay, this is when we just passed a 0 on our private key, and this is where we passed a 1. So you can leak the private key bit by bit by analyzing the power consumption of the CPU. Now, this is very simplified because obviously there are a lot of things going on, like the signal won't be always this clean, and the CPU is doing many other things. And so you will have to really analyze a lot of samples and a lot of decryption attempts to really leak the private key, but it works. Another type of side channel attack, and this has been in the news like very recently, a couple of weeks ago, it's what we call the cache attack. So modern CPUs, they will use some optimization techniques where they will try to predict what kind of data they will need for their next operations, and they will store them on their cache, which is super fast and super, like, can be accessed super quickly. And it's a kind of gamble that they make, but Apple tried to take this step a little bit further, because usually what the CPU does is look at it, is store the address of the data that it might need. But Apple takes it a step further and checks the value of the data. And if it's another address, then it will look again until it finds something that does not look like an address. And some researchers actually managed to leverage that to leak some bits of secret encryption keys because they would craft their payloads in a way that makes data look like an address. And well, it's a little bit complicated, and I didn't really understand everything of it. But if you're interested, I really encourage you to read it. It's another type of attack, a little bit complex for me, but I find it really interesting. And the cool thing is that we can't really, Apple can't really go back on this. They have this vulnerability on the M1, M2, and M3 chips, and for the M3, they managed to add a switch to tell the CPU not to perform this kind of optimization when you're doing cryptography. Like you can do it everywhere else, but not for cryptography. But they don't have this switch for the M1 and M2. Another type of attack, and this one I find it amazing, is what we call acoustic attack. It's also used on CPUs because sometimes they will emit some sort of noise when they're overheating, so it's an indication of like working hard or less hard. But this one was from last year, and it's researchers again that manage it. They managed to train an AI, an LLM, an AI to actually predict the keystrokes from your keyboard just from the sound it made when recorded with a microphone. So let's say you are on a Zoom call and you're presenting things, maybe you're logging into a platform and we see on the screen username, password, but the password is hidden, but we hear you typing in on your shiny mechanical keyboard. It makes a lot of noise and the microphone gets it. Well, with this artificial intelligence, they could recover what you typed with a 95% accuracy, which I find completely mind-blowing. But so this is another way of leveraging some sort of feedback to leak some information. Now, after seeing all this, you might think, well, that's a little bit far-fetched. Isn't it? Because what I showed you with the side channel attacks, it's always, oh, researchers discovered, so we don't really know if it's, like it's not easy to pull off. For instance, for the CPU analysis, you would need access to the power to be able to measure the power consumption. So you need to have physical access to the machine. And when I talked about the LED, the power LED, it's actually because another group of researchers managed to map the power consumption by reading the flickering of the light. And so you don't need physical access, but only visual access to the machine to be able to retrieve, to leak the data only from the flickering LED. But still, it looks a little bit odd, and even the other techniques, like it looks like we're in a movie, you know, like in a hackers movie. And as a conclusion, I want to show you this. This is a model that we call the cyber kill chain, and it's a tool that we use to better understand and map the different steps of a complex cyber attack, because it's not just about the moment when we run our zero-day exploit, which could happen like here, for instance. There are many other steps where the techniques I've shown you can intervene, like in the command and control with the DNS examples, the timing attacks for the reckon phase where you try to gather information. And actually, the examples I've shown you were taken from the malware that was delivered with the SolarWinds hack back in 2020 when a group of attackers managed to hack the update servers of a company called SolarWinds, who develops products, software for their clients. And once the malware reached the client's computers, it would try to communicate with the C2 server over DNS in the exact way that I've shown you with the fake IP that means something else. And the steganography thing about the XML is also part of the behavior of that piece of malware that was part of one of the biggest cyber attacks of 2020. So it does exist. Does it concern us as software developers? I mean, it's good to know. We can't fix all of it because some of those things are just out of our control. But I think it's good to have some sort of knowledge of all of this, and this is what I want you to leave with when you leave this room. And that's all for me. Thank you very much for staying here with me until the end. It was really a pleasure to share with you this passion that I have for this field. Thank you very much.